Can you try again?
Again. Yeah, I'm Kai Lücke. I'm software engineer at Kinvolk. Yeah, thanks for having me here. So this talk is about trace loop. Trace loop, in short, is a tool that allows to trace system calls per C group. It uses BPF and overwritable ring buffers to keep the logs. And it's an open source project hosted under this GitHub URL. And we use it in Inspector Gadget, which is a collection of BPF gadgets for developers of Kubernetes applications. So if you need to debug something with trace loop or BCC tools, then Inspector Gadget is helping in this setting. So why do we need trace loop? The problem we want to solve is that debugging distributed applications is hard, and tracing tools can help us to see what's going on. For that, strace is already a great tool, but in a big cluster, you would need to attach to every process you want to monitor and do this exactly before the event happens. So then that means you need to know when the crash happens and also pay for the performance impact if you have it always on. And to solve this, we have the idea of a flight recorder that will capture all syscalls with BPF instead of ptrace and save all these syscall events to a ring buffer without leaving kernel space. And we have a ring buffer per C group or a similar granularity. And all this only works if we have the underlying assumption that discarding old events is acceptable. So that we will only transfer the ring buffer syscall events to user space when requested. And we try to limit the global impact of tracing by only tracing a certain list of C groups, and otherwise, this BPF program should do almost nothing. So if we compare strace and trace loop, then strace is using ptrace to attach to the process, while trace loop uses a global BPF trace point. And strace has to work on a per process basis, even though it can follow children processes. And trace loop is a global BPF program, but we will filter per C group whether to trace or not, and actually also on UTS namespaces for Docker. Yeah, but this filtering could be anything. In fact, it's a global tracing that happens, and then we want to filter it. The speed should be faster than strace. That's the point of being able to always have it on. And what makes it very different is that strace is synchronous, so you will directly see the events that happen. You can't lose them. While trace loop is asynchronous, you will lose events which are old. And due to some BPF limitations, you can also fail to read some buffers when you're trying to log them. And overall, you can say that strace is very mature. You can use it for many cases, and it works. And then trace loop in comparison is currently not supporting all system call arguments well. So some arguments are simply not locked completely. And only AMD 64 currently is recognized.
Thanks. So now we'll talk a bit more about the architecture in more details. So this first schema. Okay, so let's look at the top left part of the screen. I have a BPF program on the Transparency Center. That means every time there is a new system call executed on Linux, it will execute this trace point on this BPF program. And the first thing it will do, it will decide whether to trace this C group or this container or not. And for that, it will use a hash map where the key is the C group ID in this example, or it could be with namespace ID. Whether it's something to trace or not. If not, it's an OP, so it will not do anything. or it will execute another BPF program per cgroup, a tail call that will look at the system call and save the content in a perf ring buffer. So there is one perf ring buffer for every container or cgroup that we want to trace. And this ring buffer is configured to be overwritable. So when the buffer is full, it just overwrite all the events. And it's seldom read. So user space don't read the buffer unless the user specifically asks for it.
I think, Alban, can you press on this restore slides button for people in the live stream to see the slides?
Sorry, I'm not sure how to do that.
I think the person, Guy, who's running the YouTube live stream has to do that in that session. It's not here. I think people in here should be able to see it.
Okay.
Okay, so we let Guy do it and go on.
Please continue.
Thanks.
So how would you work? How would you use trace loop? One simple way is to use it on the command line directly, telling it which C groups you want to attach to. So, for example, with the dump on exit flag, you can start trace loop. It will attach to BPF trace point, and then filter the C groups you want to trace. And then when you terminate trace loop, it will dump the BPF ring buffer and display the contents. And another way, without this dump on exit flag, is to have a continuous output. It will swap the ring buffer every second and then display the contents. Yeah, but normally you want to have a dynamic way of registering which C groups to trace. So there's a subcommand for trace loop to run as a system service, and it will expose a HTTP API on a Unix domain socket, where you can register C groups to trace, and then also list the current traces and request the trace, and finally close the trace. So the lifetime of a trace would be first the client registers a C group to trace, then trace loop will create the ring buffer and register this tail call for the C group. And then the BPF program starts to fill the buffer, overwriting the oldest events. And at some point, the client would request the trace, and then trace loop will swap out the buffer with a fresh one and process the filled buffer and concatenate it with any older buffer snapshots it has in memory, discarding by maximum size. And then we'll post-process all these events to have them in a printed form and send them to the client. This can happen multiple times, and then finally the client would close the trace. That means the ring buffer is deleted in the kernel, and also the user space trace is cleaned up. And instead of manually registering a C group, this can also be done by a systemd service. For example, before it starts, you would have a exec-start-pre command in the service unit file, for example, as a drop-in, where you will register this service C group, and it relies on a small helper script to get the current C group of the systemd service.
Another mode of execution is in Kubernetes. So trace loop is used in inspector gadget as a daemon set. So there is one instance of trace loop running on every node, and it executes the trace loop binary with this parameter. And what it does, in addition to the HTTP server serving request on the Unix socket, is to use pod discovery. That means it connects to the Kubernetes API server to get information about the pods. It looks in such org to get matching between containers and information like the C group or UTS namespace, and then it can publish a result as a metadata to annotations on Kubernetes. In this mode, we have trace that are kept for 3 hours. So when a pod starts and is stopped, when the pod stops, we keep the trace for 3 hours, so the user can use Inspector Gadget to fetch the last few pods that have crashed, for example. And then I present a more global view of the architecture. We have the trace loop process in blue in the middle of the screen. And then we have the BPF program that runs here to get information. And it also gets information on the right from the Kubernetes API server about the pods. That's because in the kernel level, in the BPF program, we don't know anything about Kubernetes pods, name, or Kubernetes namespace, or Kubernetes labels, or this kind of thing. We all know about low-level concepts like cgroups or namespace IDs or other things. So what we want to do here is to first, when we execute a new system calls, there is this syscenter trace point that is executed, and it will first check in the hash map whether either the cgroup ID, or in this case we use the UTS namespace to distinguish the different pods, to know if it is a pod that is known or not. If it is a pod that has just been started, then trace loop might not know about it yet. It's not in this hash map yet. Then it will register it. It means that the BPF program will automatically allocate, not allocate, but use a pre-allocated ring buffer index to redirect the execution flow to another BPF program and send the events in this ring buffer for each container. If it is a system call for containers that already exist, then we this hash map already know about this container. We just get the index of the BPF program to execute, and then it will use the associated ring buffer. And then the main loop here will get information about the new container that are detected by the BPF program, and but it doesn't know about Kubernetes labels. It will need to communicate with the Kubernetes server to get the pod UID or container ID, and then look in /proc from time to time to get the link between that and the cgroup to be able to match the information together. Later, when the user issue a command such as kubectl gadget trace loop show, what it will do in the end is use HTTP request to the trace loop process to fetch the trace, and that will look at the ring buffer for the matching pod or matching container. Okay. So we have this other mode of execution as a container. So that's just the same thing as presented before, but you don't necessarily need to compile trace loop if you want to trace it yourself. You can either fetch this Docker container that is published at this address and then run it this way, so you don't have to compile it and make a pseudo trace loop. Then how does trace loop know about the different system calls? At the moment, it's a kind of manual process at build time. So when we build trace loop, before building trace loop, I have a script that look in this file, so it gets the list of all the system calls and the numbers on AMD64 platform. And to know about the parameters, it looks at the different trace points that are on the trace file system. For example, there is a sysenter open that gives some information about the parameters expected there. But then there is some post-processing to do, because there are some system calls don't exactly match with the system call trace point at this path. For example, there is some system call new uname, new fstab that has to be matched with uname on fstab and so on. So that's how it works at the moment. And surely, maybe there is a better way to do it for getting information about new system calls or more programmatic way. But at the moment, that's how it's done at the build stage. There are scripts to get this information.
And the goal is to display a familiar output to what strace is doing. So you have the system call name, and then you have the arguments printed. And to do so, we need to dereference any buffer pointers. So for example, the open-add system call has the file path. And to copy this file path from the buffer pointer that's given as Syscall parameter, we have to have a way to copy null terminated strings, for example. Or sometimes for the read and write system calls, for example, we know that the size of the buffer is given as other Syscall argument. And sometimes, for example, for read, you actually have to do this as system call exit, because the return value of the syscall is the length of the string. So we either need to dereference the buffer pointer at sys enter or at sys exit. It depends on the system call. And so this is currently manually annotated. There are some other caveats like system calls that don't return or return twice. So currently, for example, in this 3 system calls, we only care about argument 1 when we think about dereferencing a pointer. And then for open add, we can do it as sys enter, reading until the null byte is hit. For write, we also do it at sys enter, and the length is given as a second argument for the system call. And for read, it's the return code of the system call. That's the length of the buffer. So the flow is, first we have this trace point, this enter, where the tail call is done for the BPF program. This will look up the system call in the syscalls map to get the correct annotation of whether whether arguments should be dereferenced and either at sys enter or at sys exit. And then it will write the first event into our ring buffer, that is syscall enter and the different parameters it got. Then it will save these parameters also to the probe at sys exit map and start to dereference any buffers that can dereference at sys enter. And then later in the second trace point at sys exit, again, we would look up the syscall that is currently executed and to know whether we should dereference any arguments now at this exit. Then we will get the original arguments for the syscall from the probe at this exit map and start to dereference any buffers, and then finally write the syscall exit event with the return code to our ring buffer. So for example, for the read and write system call, this is how it would look like. In the ring buffer, we have 3 events per syscall here: enter, parameter, and exit. And the whole goal of this exercise is to be fast so that we can have always on tracing. And we made a small benchmark here to compare how it is doing. We are running the sysbench benchmarking utility with the file.io test. And this test supports 3 different modes. The first mode is synchronous reading. So we are reading from temporary files in memory. And when we have a read system call, the buffer is locked. So that has some overhead. We will copy the buffer of the read system call to our ring buffer. And strace will also display the first bytes. That's also the case for trace loop. The first bytes will be logged of this buffer. While for the asynchronous I/O syscall, we will only log pointers. That's also what strace is only doing, simply store the pointers and display them without copying the buffer contents. And for comparison, we have, it also supports the mmap mode where no syscalls are done at all to read the file. And yeah, the baseline is having no tracer. And then we have trace loop being passive for the current C group. And then we have the case of trace loop being active for the C group. So the first case is just a knob, and then the second is a tail call to the tracing program. And yeah, we compare this with strace being attached to the process, and then we can see that trace loop being passive has a small performance hit, but it's not too big for both synchronous and asynchronous I/O. Trace loop being active has a bigger hit, like maybe up to 40–30%. And of course, it has a larger hit if we are copying buffer contents in the synchronous case here, compared to asynchronous I/O, where only the buffer pointers are logged. Yeah, but compared to strace, the performance impact is still not too high, so it's up to you whether you find this acceptable. And as said, yeah, you would decide whether you want to trace a C group or not. And for others where you don't want to trace loop can be passive with minimal impact. So what are the limitations? There are several drawbacks. The first drawback is sometimes the BPF probe read helper will fail to dereference a buffer when the memory page is not present in memory. So this happens when first time we encounter a reference. And then on the second time, this would work. So why is this so? It is, for example, the case where we have a reference into the data segment of a binary or a reference into an mmap file. And the kernel would fetch this data during syscall execution, but at sysenter, it's not yet there. As a workaround, we could try to dereference this pointer again at syscall exit. That could work in many cases. Maybe it's not valid for all parameters. And in general, there's also no guarantee that due to memory pressure, this page is still there at this exit, I would say. So, and yeah, limitations which are due to our current implementation of trace loop are that, for example, we don't detect yet when a ring buffer with syscall events is wrapping. That means old events are overwritten. That's not marked yet. And we also, because we have to merge the per CPU buffers, didn't address this problem yet when we are merging multiple per CPU buffers. This merging of CPU buffers is also a bit complicated because we have to sort by timestamps, which is maybe not the most robust way to do this. And yeah, when we are post-processing syscalls, it's not super efficient right now because we have to process the whole trace data of multiple snapshots, which could be there. Because it can be that in one snapshot of the buffer, we have this enter event, and then on the next dump of the buffer, there's a sys exit event, and they need to be related to each other. And the current length of buffer dereferencing is 128 bytes. So that's not configurable right now. And yeah, the biggest drawback is, as Alban said, we are currently annotating the syscalls manually, when to dereference and so on. And we don't have any way to detect any constants or structs yet. So the output is compared to sys, to strace, not as nice.
Thanks. So another limitation is in the way we detect new C groups or new container. In the integration that Kai showed with systemd, that's kind of a manual integration where you edit the systemd unit, and that only works when the command you write into start pre has to have access to the Linux socket of Trustloop, and it has to have the correct permission to do that. And if the systemd unit doesn't, maybe it doesn't run as root, then that will not work. And another limitation at the moment is on Kubernetes. The limitation is to take care of race condition. So it knows about the new pods or new container from the Kubernetes API, but that API is not synchronous. So it might be that a pod is deployed on a node, start to do system calls, even before the API server has sent the information, the signal that there is an update on the pod. That means that the BPF program will run before there is any information from the Kube API server. And to be able to solve that, we at the moment we trace, we pre-allocate a pool of ring buffer on BPF program to attach dynamically in a BPF program. That will be a lot better if we use a synchronous way to get information from the container that are running directly on the node. And that will be possible with OCI hooks. So OCI is it's a specification, OCI container runtime spec, to describe how the container is executed. And in there is a specific, it is specified how to run hooks before and after a container is run, and that run in a synchronous way. So that will be possible to use that to get information about the new container in a synchronous way and register BPF program at that time. But the integration of that in Kubernetes is not perfect yet. That depends kind of on your container runtime. For example, on Cryo container runtime, there is a way to add a configuration droplet to say, I want to execute this script that will talk to Trustloop, but it's not generic that it works with all container runtime. We have tried to make kind of a hack on RunC, where we hardcode hook to send a message to Trustloop. That works fine on our Linux distribution, but that's not a generic solution. So at the moment, we have this limitation. Another big limitation is the memory usage of Trustloop. So first, when I said before that trace for a container is kept for 3 hours on Kubernetes, at the moment it's kept in memory, it's not saved to disk, and that can accumulate and use a lot of memory. But while the container are running, we use a per ring buffer, and that's a per CPU ring buffer. It means if you have a lot of CPU on your machine, that will multiply the amount of memory needed. And we, at the moment, pre-allocate the amount of container we can support to 128, which is an arbitrary number, because we don't have this way to dynamically get the thing we want with OCI hooks, as I described before. So if you do the math, at the moment it's configured to use 64 pages if there are 4 kilobytes, and if you use 16 CPU, each of them have their own ring buffer, and 128 containers. That's actually a lot of memory that is non-swappable memory that Trustloop use for ring buffers. So that's a lot of memory to use even before you can strace anything. In comparison to strace, that's really bad in comparison. So that's something we want to fix. So this is how per ring buffer works. Each CPU has its own ring buffer, and since each CPU has its own ring buffer, it has been implemented without locks, so the CPU can write into its own buffer without locking. So that's quite fast. That's good. That makes things more complicated in user space because the user space has to get information from many different ring buffer and look at the timestamp and reorder it. And that's a bit more complicated. That's things I've got wrong in the past. If I look at the one ring buffer of size len from 0 to len, it works with two pointers. There is a read pointer and a write buffer pointer. And when you add a new element in your perf ring buffer, you add it at the write pointer, and then you update the write pointer. And then concurrently, read pointer is updated when the reader reads. So read and write go in the same direction in this way. That's how it works with these system calls. And you can see that we use mmap with read-write page memory. That's how perf ring buffer works normally, but there is a different way to use that. We can use that with configured as a backward and overwritable ring buffer. That's what it uses in trace loop, because we want to make them overwritable. So that's how it's configured. We have a single pointer. So whenever it needs to write, it starts from this pointer, it add an element before and update the single pointer, and so on. And when we want to read, we have to stop the writer. Either we copy all the buffer and we stop, so the writer doesn't write at the same time. And then we start from this single pointer and read everything and put it in the order to fix the order. So that's what trace loop is using at the moment, this perf ring buffer configured in a backward and overwritable way. But there is a new BPF ring buffer that happened in Linux 5.8. So that's a single buffer for all the CPUs. So in order for them not to write over each other, there is a lock that is used. It works in two stages. First, writer has to reserve a region of the buffer to write into. That's done using a spin lock. And then it commit, that commit can be done without locks. And then for user space, that's a lot easier because it's there is a one buffer to read from, so there is no reordering to do. So that's cool. And for me, for trace loop, that will be another advantage, that it has only one single buffer, so that will use less memory instead of having an amount of memory that depends on the amount of CPU you have. And because we use a lot of them for each C groups, that is a lot. Okay. Another limitation of trace loop implementation today is that it doesn't know about all the constant and struct that it does read. For example, if you look at this open apt, this constant is not meaningful for the user. Strace know how to decode it to write at fd cwd, but yeah, in trace loop is not done. And another example is receive vfrom. Trace loop doesn't know about the struct message header, so it just prints the pointer, but that's not really useful for the user. I would like if I've not looked into it, but I would like if BPF type format will be able to help with that in an automated way. It's probably more expert in the room who knows about that. So to conclude, what are the things that can be improved in trace loop? We could use this new BPF ring buffer to simplify and use less memory. We could have a better integration in systemd. We could have a better integration in Kubernetes as well, using OCI hooks instead of this current way where we pre-allocate a lot of containers. Sorry, we can pre-allocate a lot of perf ring buffer for future containers and do that in BPF. And we could know more about all the system calls, maybe using BTF if that's the correct way, or maybe using something else. Now it's time for questions. Thanks.
Okay, thank you very much. If we have any questions for Alban and Kai, please step up and state them now. We can ask questions either with the microphone or in the public chat. I'll repeat anything that is stated in the public chat. Brendan just asked where his question should be asked, and that's why I just sent this. And I noticed that Arnaldo in the shared notes put some examples of how to use some of the BTF and perf features that you were discussing earlier, so people can go check that out when they have a chance. I see some people typing in the chat. So David Ahern asked, did you compare the performance against perf trace?
I have not checked. I don't know if no.
Yeah, but it's something good to add, maybe.
Do you expect it to be better or worse?
David Ahern said it has much lower overhead than strace. So maybe something to look into.
So the difference between active and passive trace loop, the difference is that trace loop is always registering this BPF trace point, but in the normal case, it will just directly quit working if the C group ID is not to be traced. So, and otherwise, if it's to be traced, then it will do the tail call and run the real tracing program. So the difference is, actually doing something or doing a no-op.
The next question is, did you look into LTTNG system call tracing? It fetches data from user space as system call input output.
No, I have not looked into it. I'm not sure to understand what does that mean to look as a system call input output.
Brendan Gregg asked, how does this tool fit into the ecosystem today with BCC and BPF trace?
So it's currently a tool that is independent from BCC on BPF trace. It uses GoBPF, which is hosted at github.com/iovazor/GoBPF. And the feature that it needs that are currently not in BCC are the possibility to use perfring buffer in the backward and overwritable way. I don't think BCC has that at the moment. At some point, it needed to use some maps type, but I think now it's fixed in BCC. So I don't think there are other features that are missing from BCC if you want to use BCC for that. But sorry.
No problem. Please continue.
Sorry. No more.
So Matthew clarifies that LTTNG fetches data from user space. The pointer to a file name string is saved as a string, not as a pointer into the trace.
Yeah, that's also the case for trace loops. So in BPF, it will dereference this user space memory part that is pointed to by the pointer. And then this will be saved into the ring buffer.
Great. Okay, we still have 5 minutes left. Does anyone else have any questions for Alban or Kai about their presentation? It looks like Brendan is typing again, so let's give him a chance to ask his question. Are there plans to support more than just system calls?
No precise plans. There was something I was looking at some point to look at the capabilities to know. It's a bit similar to the capable tool in BCC, which say which capability are exercised by the process. So if a process tries to do mount, you will see, oh, it tries to use capsysadmin or something like that. and I wanted to have a way to see Kubernetes pods, what are the set of capability that it tried to use and record that. So there was some code in Traceloop trying to do that, but it's, yeah, I don't think it's complete or it works. More than syscalls otherwise, but do you have a more specification? What kind of events are you looking for?
If you browse the BCC BPF trace tools, you'll see trace points, K probes, U probes, etc. I think that's the area he's concerned about.
Okay. So in Traceloop, I didn't have plans to use more things, but in Traceloop is one gadget that is part of Inspector Gadget, and Inspector Gadget use other things. It reuse the BCC tools, and it so in the other tools, then it make use of kprobes, not uprobes yet, but that's something I would like to have. But that's a different use case than Traceloop, but I want to have something always on. I don't have ideas of use case where we would want that, but I'm interested to know if you have specific ideas.
Yeah, but in general, this principle could work for all the other tools in BCC. Instead of directly writing to a normal perf map and then reacting on user space to the events, you could have this overwritable ring buffer and log as much as fits into it, and then later decide to read it out. So that's just a general principle that's different from the existing BCC tools.
Okay, we have a minute or two left. I'll let Brendan finish. Brendan says there's another always-on system call tracing product I'm not mentioning, and while you can do a lot with it, I always thought it was limited due to its event sources.
By its event sources, do you mean that it's too much data to handle, or do you mean that it doesn't get enough information?
Yeah, okay, because it's limited to syscalls, it's not that useful because it's not flexible to attach to anything else. That's
Right.
how I understand this comment.
I think that's what he's trying to state as well.
Yeah, but as I said, this is a general principle, and yeah, you could also change other tools to use this principle of having an overwritable buffer, which is always on.
I guess we're always in this situation where, do I want to make this tool very good at the one task that it's assigned to do, or do I want to make it generic enough to take in any kind of event whatsoever and then become a more generic tool, but not specializing anymore in the specific task it was originally designed for?
At the beginning, it was thought to be used on Kubernetes, but then Kai came up with this idea of integration with systemd that is useful as well.
All right, Albert and Kai, thank you very much for your presentation.
Thank you.
Okay, I'll take back the presenter now, and we'll load up the slides for the next presentation. Okay, and I'll make Joe the presenter. Meanwhile, I hope Guy can said he's going to restart the YouTube stream and try to get the slides working properly. So get that going. Hey, Joe, you should be the presenter now. And wait a minute. Let's see. Hi, Joe. How you doing?
Hey, Dave. I'm doing well.
Great. All right. Guy says that the live stream should be good with the slides are showing again. So, Joe, you can start whenever you're ready. Oh, by the way, everyone, please keep your mute on. Keep your mic muted during the presentation unless you want to ask a question or something that helps everyone out. Thank you. All right, Joe. Thank you.
All right. So my name's Joe Stringer, and I work on Cilium, which is a piece of software that provides networking security and observability in cloud-native environments. So in the preparation for this talk, As you can imagine, I did a lot of internet searches, and one of the sort of thoughts running through my mind was, how is the internet held together? Because I mean, I always had some sort of notion that maybe it was duct tape or pixie dust, but I guess what I'm going to talk about in this talk is really, does the SKB mark have a role here? And while I'll focus on cloud native, because there's a bunch of new software plugins for controlling the network that have been built in the last sort of 5 years or so, I think that based on the use cases you see, this may be a bit more widely applicable. So to give you a brief overview, I'll go through a bit of background, talk a little bit about the mark, the different names for it, and how it's used, I guess how it's defined and so on, and then bring a bit of context on Cilium and how the cloud native space works here, and then lay the groundwork for how I'm going to talk about the use cases that these cloud native tools are trying to implement in the networking layer. And then based on those use cases, I have a few observations. There are some challenges, particularly when it comes to building user space software that's interoperable with one another and sharing control over the Linux networking stack. Yeah, so first up, the mark of the beast. So the mark comes by many names. I think the first one here, I'm not sure if it's firewall mark or forwarding mark, but this is the usage that tends to show up in IP tables and in the routing layer. On a related note, you have the CT mark, which while that doesn't actually exist in the SKB, the usage tends to be that you will store some value into the con mark and then restore it back out. And when you restore it back out, you're naturally going to populate the SKB mark and then match on that in some subsequent logic. So while it's not strictly the same thing, it is strongly related. Obviously, you can call it the SKB mark. That's where it lives. We have the socket mark from the socket layer, so that user space applications can be programming and passing some sort of metadata into things like netfilter and TC and so on. You have the IPsec transform subsystem, and I also noticed that in OVS and OVN, packet mark tends to be just the name that they use for effectively the same concept here. So what does this mark represent? So the beauty of it is really it means nothing until you configure it, and you can define the semantics around it. So it can mean as much or as little as what you want. Unfortunately, the sort of the flip side of that is that really depending on how you're using it, it's just kind of magic. When you're trying to program how the Linux stack's going to behave, how it's going to interact with this mark, if you're not intimately familiar with the other software that is running on the system, you may just find that, oh, when I receive traffic in this particular portion of the system, it just has these bits set in the mark. And then on the flip side, when you set some bits in the mark, you may be pleasantly surprised to find that your traffic just disappears or goes into a black hole or is natted or all sorts of things. And the unfortunate thing I think here is that there's not really a centralized registry that will allow you to even necessarily discover what other software could be using the mark, how that software may be using the mark. And so making an informed decision about which bits in the mark you're using for your application and how you use those in a way that doesn't conflict with other software, that can be quite difficult. So there's no centralized registry that is until 2020. So about a month ago, Dave Anderson posted this tweet. So he sort of figured that if you create this registry on a GitHub repository, this is not going to control how the mark is used. It's not going to be a decision committee, but it's going to be a form of documentation. And so if you are using the mark, I would highly recommend that you jump on that Git repository, check out how it's formatting, how it's talking about the mark, and add in entries there for which bits are being used by your particular software. So in preparation for this talk, I walked through the cloud native world, many of the plugins there, and sort of added those usages. And in the rest of this talk, I'll sort of talk a bit more about those as well. Next up, why am I interested? As I mentioned, I work on Cilium. Cilium provides a range of different features, as you can see based on the slide here. But one of the key points here is that you can enable and disable different functionality that Cilium has. And many of these pieces of functionality in the background are supported in some way by the SKB mark. And so if you can disable or enable certain functionality depending on your deployment environment, some other piece of software may be providing those features that you're disabling. So one of the integration scenarios here is when, for instance, a user has a cluster already with another networking plugin, and that provides maybe the sort of L2, L3 piece, and then they're interested in getting some of the observability and security properties that Cilium can provide. And so in that case, we're basically needing to ensure that both of these software have a common understanding of how the kernel is handling the packets to ensure that we're not going to drop packets when it follows a particular path through the system to achieve some of these goals. And so what I looked at in this particular talk is broadly is the logos that you see on the screen here. These are all projects that are listed from the Cloud Native Computing Foundation's website on the landscape of networking plugins. I didn't bother looking into any proprietary plugins. I don't think I could find the source for them anyway to figure out what they're doing. Yeah, so I think there's a couple of cases here. So AWS, I just put the logo there because they don't have a specific logo for their plugin, but they have the AWS CNI VPC Kubernetes plugin, and they also have a service proxy plugin. So I kind of grouped them together there. And OpenShift is using OVN and OVS to do forwarding there. So you can imagine with any of these various different plugins, they may be providing some feature, and from a Cilium perspective, in some sense, it would be nice if we could just provide Cilium in a way that will interoperate with any of these other software, regardless of how they're using the mark. So this is not necessarily a terribly scientific kind of an approach, but broadly speaking, the steps kind of went. You look at the CNCF landscape website, you find a project, you look up the source code, search for the various different names of the mark, and see what you can discern from how they're using the mark for what kind of use cases they're looking for. And yeah, so I'm going to talk a bit about the use cases next. So I have collected together 7 specific use cases here. And I'll walk through them in terms of how many bits are needed for this feature, which networking subsystems that these bits are being passed between, and maybe some interesting use cases on the side where maybe a particular plugin takes it a little bit further. So one you can't get away without, I should say, in the Kubernetes world would be with the network policy. So by default, Kubernetes will ship an IP tables rule which will drop traffic if you don't otherwise route it to accept that traffic in your IP tables chain. So there's one bit in that case where there's this drop bit, it'll be set one chain, and then at a later chain it will be checked, and then if that bit is still set at that final point, then the traffic will be dropped. There are other variations here where the policy may be to match on some traffic and then set a bit to allow, and that may be from a policy perspective, or there may be a sort of a policy skip aspect there as well. So I think in the encryption cases, there's a case where you would match on some set of traffic, make sure that it is an ESP packet, and then set a bit, and then that would allow that next through to the next stage. So if the traffic comes from a node that is, you would expect encryption to be applying, but it's not applying, then you would drop that traffic. One of the common use cases here is really to store some complex path through a chain of rules, and use that as a way to set the mark, and then later on, depending on a wide range of these rules which may set the mark, later on you'll do something with that. You'll either drop or allow. And by structuring it this way, you can have some logic in between those 2 points, the point where you set the mark and the point where you interpret it. So I talked a little bit about encryption before. Typically described as 2 bits, one on the encrypt side and one on the decrypt side. So one approach is simply a request to encrypt this traffic and a request to decrypt this traffic. There was one plugin that was quite interesting. They actually mentioned that on the encrypt side, it's not necessarily that they want this bit to represent, please encrypt this traffic, but rather they actually talked about how when they send traffic over a VXLAN tunnel, the port was no longer available to the transform subsystem. And so what they would do is match in an IP tables rule on the destination port, set this bit, and then use that bit as part of the lookup in the IPsec lookup. So I found that kind of interesting. I don't know if there's something else that could be done for that particular use case. But yeah, so broadly, we have different combinations, either taking state from netfilter or taking state from eBPF and then passing that into transform, into IPsec subsystem. And the variation here I'll talk about is where you may want to have a range of keys active potentially at the same time, and then use a index to choose which of these keys you're going to use. So this is helpful for key rotation and so on. Virtual IP. So in Kubernetes parlance, this may be called services. It's also related to load balancing here. So in this case, a service may be some IP address and port maps to one or more backends. And some of my colleagues will be talking, I think, on Thursday about how services are implemented in Kubernetes in much more detail. That's not really relevant for me to bring up here, but typically this will be defined as one or more bits to request DNAT. Strictly speaking, you don't necessarily need to. I mean, you can just write some sort of logic that matches on the destination address and port, and then applies the DNAT logic. Yeah, so in the Cilium case, I think if you deploy on an old enough kernel, then this functionality may be limited in terms of how we implemented in eBPF, and so we'll integrate with another piece of software which will provide that same functionality. I did notice one of the cases was in an OVS bridge where there would be some sort of a match on the destination addresses, and they would set this bit, and that bit would be passed to the policy routing configuration to then route traffic back into an OVS bridge to then apply the DNAT. The most complicated use case I saw here was, I think, kuberouter, which when they configure the kernel, they will look at the service and take the 3 tuple of the IP address, destination IP address port and protocol. They would hash that into 30 bits, and then they would set that in the mark. So there's an IP tables rule that has that 3-tuple match, and it sets this this mark, and then in IPVS, it would then make use of that mark in some way to do some sort of load balancing. So IP masquerade. In this case, so depending on the plugin, the networking plugin in Kubernetes, the pod range, which provides the network connectivity for your applications, that may be, for instance, an RFC 1918 address space. It's not necessarily publicly routable, although that does vary depending on how you configure things. And so in that case, if you want those applications to be able to reach out to the internet, you need to somehow give them a public IP address. And so that's really what this use case is about. Typically, this is, again, one bit just request that SNAT will apply to some set of traffic. The matches here may vary, so it may be match on this particular range and then please apply SNAT, or it may be please match on this range and then skip the the SNAT, sorry, and then in that case, SNAT will be applied by default by a later rule. One of the more interesting use cases here was actually where one of the plugins provided a configuration mechanism by which you could write YAML that says applications with a particular label should egress the cluster with this particular source IP. So you could imagine having perhaps 3 different applications on a given node, and then you have perhaps 3 IP addresses associated with that node. And depending on which application is sending traffic out to the internet, it will be masqueraded to a particular IP address. So although that's not strictly kind of in the cloud native world, I did notice while I was searching some use cases here around VPNs. So for instance, you may receive traffic onto the node from a VPN, and then you will mark a bit to apply SNAT if you're going to forward that traffic on to the local network. So that way the replies will come back through this node and will be able to be routed back out to the VPN. So yeah, so broadly, I kind of see a couple of sort of paths through the stack here. You have kind of eBPF or OVS or NetFilter passing some state onto the NetFilter subsystem. Later on, there's also some eBPF through the stack to eBPF cases as well. Multi-homing is quite interesting. Here, the most common case I think in the cloud native world would be in a AWS environments. So for a bit of background here, you'll typically in something like EKS, you'll have a primary device which provides network connectivity to the outside world, and then you have one or more secondary devices. I call them secondary because they're not the default route per se. And these secondary devices will have some number of IP addresses, typically I think up to maybe 8 IP addresses associated with them. And then when you deploy an application on that node, it will consume one of those IP addresses associated with a particular secondary device. So when you want to deploy more than whatever the maximum number for a given interface is, you'll need to request another secondary device. And so you may have some number of networks attached. And one of the interesting points here is that in this case, there will be source routing applied. So when an application transmits towards a destination within the cluster, it's going to need to egress that traffic on the device associated with that particular application. And so by default, the policy routing would say match on the source address and direct out the secondary interface. But when you get into implementing services and so on, you have outside traffic attempting to reach into the node to reach the application. This can cause trouble because your inbound request would come in fine. It would reach the pod or application that you're targeting, but then when that application responds, it will then respond and get routed out through the secondary device onto the private network. And so you don't end up with two-way connectivity. So the use case here is really a classic ConMark use case where as traffic comes in on the primary device, a bit is set in the connection mark. And then as the replies come back out of the pod, they'll do a connection tracking lookup to restore that mark. And if the mark is set, then that's basically a signal that the routing should be performed back out the primary device. And that way you've established your connectivity. Again, in the sort of VPN use cases, I noticed some other cases here where maybe you'll have a management agent on the node which configures the VPN networks. And so there, you don't want to send your management traffic over the VPN that you've just provisioned. And so you'll set a mark in the socket mark, and that way you pass that state down into the routing layer, so it can decide how to route that traffic. So by default, you'll go over the VPN perhaps, and then management traffic will not. Application identity is quite interesting. So in a Cilium cluster, each endpoint has an associated identity. And this identity is typically a 16-bit like integer. If you're running multiple clusters, then this would seem to expand out to 24 bits. And so typically this is used for applying network policy. So if you have one pod on the node and it transmits traffic towards another pod on the node, then at the source, you're going to do an evaluation of whether the source is allowed to reach to the destination, and then you'll apply a identity-based policy there. And then the traffic will be passed through the stack and will arrive at the destination. And then again at the destination, it will have its own policy to determine whether the source is allowed to actually send traffic and whether the destination is allowed to receive that traffic from that source. So one of the nice things about tying this into something like a ephemeral identity that you're associating with the packets as they pass through the system is even if there's SNAT or anyone's messing with your traffic in between, the idea is you have a stronger identifier that tells you what the true origin of that traffic is. So this becomes a little bit more interesting when you start to get into integration cases, which is typically how this will fit in. And so you'll apply some other piece of software in addition to this mode, and that software could be doing just about anything. So it may be routing traffic in a particular way. It may be applying what we call port map, which is where there's a particular port associated with the host is mapped into a pod or application I guess destination. But this could even just be like integrate with customers' random IP tables configuration. So you don't necessarily have a lot of guarantee about what's going to happen to those packets in between. Yeah, so typically passing state between from eBPF and NetFilter through the routing system, and then arriving and being interpreted at a destination eBPF program. My final use case here is around service proxying, where you're applying L7 termination for traffic in your cluster. So typically, this encodes at least 1 bit worth of information. And the common one is when this traffic is going out or when this traffic is coming in, you want to selectively redirect this traffic to the local stack so that the service proxy that is running there will accept that traffic. There's different variations on this. Unfortunately, most of the service proxies I saw actually tended to configure the full mark for this use case, even though they really only have 1 bit worth of information. I did note one of them decided it would be interesting to use the mark 1337 because I guess they're more elite than the rest of us. More complicated use cases here. In Cilium, when interoperating on older kernels, we'll pass a 16-bit T-proxy port through the mark from eBPF through to the NetFilter subsystem. So that way we can choose which transparent proxy port to direct this traffic towards. Later on, there's also, assuming that you're handling traffic, from some source through the L7 proxy, and then that L7 proxy establishes an upstream connection out to the actual destination. Again, we have this sort of application identity aspect from the previous slide, where you may want to pass that identity up through that proxy, and then from that proxy, pass that identity back down again, so you can retain that state throughout the entire packet flow. Cool. So the next section of the talk is about some of the observations from commonalities of these use cases, and some of the challenges for writing software that interoperates between with other network applications that are also programming the stack. So one of the basic questions is how do you actually allocate the bits in this mark? So in some sense, you have two extremes here. On one side, you can say, if we allocate on a bitwise manner, each bit can have some semantic meaning. And given 32 bits, you can have up to 32 features that you're enabling or disabling. And so if you have multiple applications that are using the mark, you can say, oh, you use this one bit, and you use this one bit, and you can sort of divide up the space in that kind of way. In practice, what that means is that if you're strictly following that, you only have 32 features that you have available to you. So on the other extreme, you would have the entire mark used, and so you have arbitrary values within the 32-bit space to deal with, and so you have a much larger set of possible values you can configure. So in theory, 44 billion different excuse me, features. Although the one thing I note is that, at least from what I could tell, anybody who used the full mark tended to only use one bit worth of logical information, and just unfortunately it's just written not in a way that would interoperate with other software. So you may have noticed that I mean, while many of the features only use one bit for the basic implementation, if you wanted to do the more crazy and interesting things, then you're quickly going to add up to more than 32 bits worth of information that you want to pass between subsystems. So taking some inspiration from the previous slide, so you can, of course, encode some meaning in a bit range. So if you have 16 features, then maybe you can use the lowest 4 bits to encode different values for those features, rather than using the lowest 16 bits and enabling each feature on a bitwise manner. There are some limitations here depending on which subsystem you're integrating with. You may or may not have the ability to do a match and choose which path based on a set of values within this, but it is a technique that can be used there. The other one is naturally you can start to overload the bits, right? And so, for instance, on egress path versus ingress path, you have the same bits have a different semantic meaning. You can take this a little bit further, and depending on how the packet is sourced or destined, maybe packets destined to IPs within this range use these bits for this semantic meaning, and then packets outside this destination range will have another different meaning for the same set of bits. So depending on how, I think, low in the stack you are, you might be kind of intrigued at this point, or you might be have kind of more of a visceral reaction to this. It certainly introduces some interesting challenges if you are starting to overload the mark there. So while in theory, it would be lovely to be able to just build some software that would interoperate with arbitrary other pieces of software. From a practical viewpoint, it makes sense to start from somewhere. And this is one of the themes that I noticed when looking at the particular software that I've highlighted earlier in this talk, where because all of them need to interoperate with Kubernetes, the fact that Kubernetes adds an IP tables rule that sets, that uses bit 15 to drop traffic means that every other plugin needs to respect those semantics, and everybody avoids that mark. So in some case, in some way, that's maybe an example of the semantic sharing working, because everybody will actually have that same common understanding of those particular bits in this case. In terms of Cilium, this tends to be driven by existing users who are running other plugins and they want to deploy Cilium on top, and so there we start to explore how we can share those bits and what meaning those bits have, and whether you're enabling particular features or disabling particular features when running in conjunction with other software. And so one of the key points here would be like if you have a clear distinction of, let's say we have the 7 use cases there, and you want encryption, and maybe your underlying plugin already provides encryption. So in that case, from a Cilium perspective, we don't need to turn on any of the encryption handling logic. And so maybe we'll save those bits and help to interoperate there. If it's unclear which piece of software is responsible for a particular network feature, then that's obviously going to be a bit more tricky to figure out how to reason about. But from a practical perspective, this is not necessarily free in terms of either developers trying to set these things up and figure out how they work and build the software to be interoperable with other network software. And it's also something from a complexity perspective and how you manage deployments. There's just more moving components. There's more things that can go wrong, and it's more difficult to debug. And so on this kind of complexity aspect, I mean, I've tended to focus a lot of this talk on how the bits are used and the semantics of how you share the bits between applications. But in practice, the mark is not the only integration point for this software. So different plugins are going to be configuring IP tables rules to match on specific destinations or sources, or maybe they'll interpret the mark to do policy routing in different areas. So the set of bits that you actually use to implement your feature is more than just the 32 bits of the mark. You may be matching on packet fields, you may be matching on connection tracking state, and so on. So ultimately, you end up needing to sit down with the network stack diagram and understand not only the packet flow of how packets go through TC and eBPF and NetFilter and so on, but also how the different software programs those different mechanisms and the different paths that packets will take through those different subsystems depending on the features that you have enabled and depending on the source and destination of the traffic and so on. So one of the most common ones here is somehow the forward traffic seems to typically work, but it's always the replies that disappear somewhere, whether they're being routed to a different device in the multi-homing case, or whether they're being masqueraded when the inbound traffic was should in theory when you reply, you should be able to use the same tuple as the traffic that was coming in. And then when you introduce L7 proxies here, it can become particularly interesting when you get into the transparent proxying case, where you have the same tuple as used for both the downstream and upstream connections. And so just because you see a particular 5-tuple used in a packet at a particular device, it doesn't necessarily tell you whether it's the connection establishment for the sort of source side or whether it's the destination side. So maybe that sort of last section kind of gives you a hint as to whether the overload approach to the mark is a viable approach from deploying network software that uses the mark. And so like the natural question that comes up there is like, well, what if I had a few more bits to work with? And so this is an area that there's different ways we could imagine providing more bits. One of the areas that we're actively looking at from a Cilium perspective right now is on consolidating subsystem usage on eBPF. So this way, rather than transferring sets of metadata from eBPF through to NetFilter, through to the routing subsystem and so on, if we can implement that logic natively in BPF, then we can use standard tools that we use in the eBPF realm, and we can reason through the paths there and so on, and minimize the usage of the mark. And that way, when we do want to integrate with other software, those mark bits are not already reserved. And yeah, and so this doesn't have to be eBPF. If you're using OVS, maybe build more of your logic in OVS. If you're using NetFilter only, maybe consolidate there. One of the questions that came up while I was discussing this was whether we could just extend the mark space. Now, I don't imagine that you would be able to just take the SKB mark and extend it, but one of the ideas would be to add something like a SKB extension, which maybe you choose in certain circumstances to be able to extend the SKB to have more generic bits to work with. Alternatively, another approach would be to formalize some of the use cases. So maybe some of the use cases that I presented in this presentation here, or maybe you have other use cases for applications that these applications may want to integrate with. If we formalize some of those with their own dedicated API, then that may free up some of those bits that people use from this generic space by defining those semantics. And there's one example I saw here of what I think is called the sec mark, where basically there's an IP tables target to set the SE Linux security context, and then you can basically allow a drop traffic based on that. And so this is, as far as I could tell, it's not using the common SKB mark space, but rather it has a dedicated function. So to wrap up, so the mark is a powerful mechanism. It allows transferring, all sorts of different state between different subsystems, and there's a lot of freedom about how you define the semantics around the mark. But the flip side of that is, of course, that means that any user space applications that want to share the mark and build interoperable software need to then come up with conventions and agree upon how those mark bits are used. And so that really drives a lot of the uncertainty where when you're trying to implement some new feature, you realize the mark is useful for this particular use case, but you don't really know, can I just use this bit? Because it's not until you start to deploy in environments that look more like a user environment with whatever software they happen to be running, it's not until then that you really find out who's using the mark in what way. And so I hope that the forward mark registry that I've mentioned earlier in the talk will help in this way, and that if people like you are contributing usage of the mark into a centralized repository, then hopefully we can at least have a starting point on which projects may overlap with my usage of the mark, and from there you can investigate this particular project and decide whether it's even relevant for you to integrate with that software, and how you might share the marks with that. And overall, yeah, I mean, it's clear that there's more uses than there are bits in the mark, and it's really just a matter of which features you want, and yeah. So I'd be interested to hear from you. Is this a pain point for you? How are you using the mark? Did I miss some use cases, and so on? And I've provided some links available here for you to look at. That's all I have.
All right, thank you, Joe. Two quick points I'll make. I noticed the application ID thing. Android does something similar, whereas they concatenate the UID with the application ID, and that feeds into the fib rule lookup table, and therefore you could say when user X uses application Y, go over to VPN, and so on and so forth. So I just noticed that little parallelism there. Perhaps one mistake we made when we added the SKB mark is we just had this 32-bit opaque thing, and there's no way to kind of contextualize the value. So you had to go through all these different use cases and kind of figure it out yourself. So perhaps the thing we need is some kind of context ID, or what that really evaluates to semantically is a type. So it was some kind of ID that says what's in the 32-bit value, and therefore you don't have to play this guessing game, and you would know what was there contextually. But then the challenge is teaching all the infrastructure to use this ID to start setting it, and so on and so forth. But in the long term, it would eliminate this patchworkness of figuring out what the SKB mark actually represents in any particular point in time and how to work with that. So looking further down the road, then your eBPF programs could check the type and say, if it's this SKB mark is of this type, I know how to handle it, or I don't, or so on and so forth for transformations. So that's just my idea. Some questions. Jesse asks, why only SKB mark? Does it have to, because it has to exist everywhere? Like, well, why is it specifically interesting?
Yeah, I mean, there are other bits, I think, in the SKB. I think this seems to be the one that's universal, that every different subsystem has somehow integrated with it. And I think that's kind of the value, and that's why it is interesting, is that it's passed everywhere. And everywhere has some capability to match on it and implement some logic.
Yeah, there's a lot of infrastructure that exists that uses SKB mark as a way to key in one way or another. So therefore, it's kind of universal as a tool.
Yeah, and you brought up sort of the semantic meaning of a type, and I think one of the things that occurred to me recurring throughout this was, in some sense, this is like a stack variable. Right, like, and particularly like someone like use cases, it's really just net filter to net filter. So all I need is like this extra little bit of space that I can stuff something into, and so it's quite interesting to look at that from your kind of suggestion around the semantics of saying, well, now that variable has a type.
Right. In a way, it's kind of like the SKB control block, like who owns it, what values are there, and like, you know, what is the type of the item inside. And it's a similar set of like having to audit all the use cases and the control flows and define ownership rules and things of that nature. So it's a very similar problem space. Cool. Is there anyone else with any other questions? We have 2 minutes left for our break. I don't see anyone typing and coming in.
And I'm happy to take this to the hallway track as well, if you're a little too shy to talk about how you're using or abusing the mark today.
Yep, we have the hack rooms. You can use them. You can go in there to chat with people and things of that nature. So feel free to use them, all the infrastructure they have here for this conference. All right, Joe, thank you very much for your presentation. It's great.
Thank you.
Okay, make myself the presenter again. Okay, now we're up to our break. And all right, we're on a break for half an hour. It starts up again at 9:30 Pacific Standard Time. Go do what you have to do, get some coffee, take a break, make a snack, go for a bike ride, whatever makes you feel better. And we'll be back at 9:30. Okay. I'm bored, so I started a poll. Oh, are you enjoying LPC 2020? You can let us know. Just a full heads up, when someone does a poll, the presenter, whoever has the presenter privilege can do a poll. You can see what people answer, so if you don't want me to know what your answer is, maybe you shouldn't participate in the poll, just full heads up. But when I publish the results, after some time, it just says how many people said yes or no, and a percentage. It doesn't say what people's responses are specifically, but I will know. Looking for something to do, you can mention Linux Plumbers on IRC or other social media platforms with this hashtag and that user ID. Actually, Linux Plumbers is capitalized for the user ID, so let's get that right. Also, when you have the presentator mode, you're the presenter, there are tools on the right-hand side of the blue button user interface where you can draw things like a whiteboardish kind of thing, and that's how I added this red text to the slide we're on right now for the break. There's also a button at the bottom. It turns on multi-user whiteboard, which basically lets everyone here do things on the whiteboard. I'm sure that could be kind of crazy. But anyways, that's some of the features that are available here. Okay, so next presenter. Mhm. If you're just coming back from the break, getting ready for the next presentation, we have a little poll going here on the next to the slides, asking if you're enjoying LPC 2020. Click yes or no. Thank you for participating. Kind of lets me know who's back already. We'll do that more explicitly in a couple minutes before we start the next talk. Okay, we'll start up again in the couple minutes. Clement, I'll load your slides up at the top of the hour and give you the presenter status so you can control the slides and start your presentation.
Okay.
We have a poll going. If you're just coming back now, asking if you're enjoying LPC 2020 so far. Finish that up soon. Click those buttons. I think that besides the little hiccup with the slides not showing up with the YouTube live stream, everything's been going smoothly so far. Let's finish that up. I'm going to close up the poll now. Like most people said yes. It's nice. Okay. Public chat. Let's load up the slides. And Clement. We'll make Clement the presenter. You can now control the slides. Let's wait till it actually hits 9 o'clock and then we can get going.
Okay. Hello, everyone. I'm Clément. I was an intern in the DOS team at Cloudflare, and my internship subject was an evaluation of tail call costs in eBPF. François is my co-author for the paper. I will first give some context around the problem we have faced, and then I will present the two benchmarks we have used, and finally I will conclude on some context, on some future developments for the project. So at Cloudflare, we are running our DDoS mitigation software on all our machines across our 200 POPs around the world. And the part of this DDoS mitigation pipeline is alpha drop. So it's an XDP eBPF tool that enforces rules. Each of these rules are governed by type in rule sets. And each rule set is tail calling into the next, because each rule set is one eBPF program. So tail calls are a way in eBPF to jump from one program to the next. And in particular, we are transferring the context from the first program to the next. Also, the address of the next program is read in the map and at a given location. Tail calls were affected by Red Pauline's mitigations of the spectral flow. And as a result, there was a performance overhead. Recently, Daniel Bachman introduced a patch to improve the performance of tail calls in static maps. So by introducing a direct jump. And fortunately, this applies to our alpha drop case. The patch was introduced between the patch was introduced between version 5.4 and 5.5 of the kernel. Let's go into more details of this patch. So the eBPF assembly code itself is the same before and after the patch. What changes is the x86 assembly code. Before the patch, we have Red Pauline here with the specific elfence instruction. And the patch uses the fact that the cell is static in the map to rewrite the outputted x86 assembly code dynamically. And as a result, we are able to remove the Red Pauline and hopefully get a performance improvement. We wanted to measure the impact of this patch on our infrastructure, but we had no existing well-known solution that was specific enough. So first option for the first benchmark was to use BPF proc test run. This system call runs one eBPF program, more specifically one XDP program on one packet multiple times, and it returns the average runtime for the given XDP program. The advantage of this approach is that it gives more stable numbers, and we are able to test one program at a time, but the drawback is that it's a bit different from our production setup. I have some results to present for this benchmark. So all the numbers from this presentation comes from tests carried out on one of our machine from the 9th iteration. The details are in the public blog post linked down the slides. This machine has 96 cores and a maximum frequency of 3.5 gigahertz. We want to measure the cost of a tail call, but with what I've outlined, we are mainly measuring the time spent in an eBPF program in total. So we use the trick to evaluate the time spent in tail calls. We can compare two scenarios. one scenario with two eBPF program with one rule in each, so two relatively small eBPF programs, and these two programs will be title calling into one another. And the second scenario is merging the two rules, so the same code, in one eBPF program. As the number of instruction is the same between the two eBPF program, we can compare the two scenario, and the difference is the time spent in the various tail calls. Unfortunately, with only one tail call, the results were not very it was not very visible, so we used 20 eBPF programs, so 20 rule sets of one rule for the first scenario, and for the second scenario, we used 20 the same rules in one eBPF program. So on average, the time spent per tail call dropped from 25 nanoseconds to 5 nanoseconds with the introduction of the patch. We can see this difference in the graph at the top, in the blue graph, and in the graph at the bottom, we see that on the case where all rules were merged into one eBPF program, there is no significant difference between the two versions of the kernel. As we have seen, this setup is a bit different from a production setup. So we created a second benchmark using two network namespaces. We generate traffic between the two network namespaces using iPerf. And we deploy L4Drop and also our XDP-based load balancer and sampler on the receiving side, so on the network namespace receiving the traffic. And with using kernel probes and some eBPF code, we are gathering metrics as we go. So we place a kernel probe on the function called VETH poll. We gather, so some eBPF code is executed when entering the function and when exciting the function, and the difference is stored in a map. This function we have kprobed, unfortunately, has some code around the function actually executing the XDP code. So there is some constant overhead around the function running the XDP code, which is the function of interest. And this so this results so in the code surrounding the function of interest, there is some part that is conditional, and this results in two clusters of values around the threshold. So in the end, this was accounted for by using free maps to collect the averages. One for the first cluster of values, one for the second cluster of values, and one for all values. This second benchmark has the benefits of being more production-like, but the main drawback is its complexity and the fact that the figures obtained tend to be less stable, in part due to the surrounding code we have just talked about. On the same machine, we can, with the same scenario, so with by comparing an eBPF program, merging all rules and a set of eBPF programs cycling into one another. But by comparing these two, we have a gain of roughly 20% with the patch introduced in kernel version 5.5. These two graphs are on global averages. And we can see a significant drop in the CPU time used in the case where we have tail call, and no significant difference between the two kernel version in the case where we have no tail call. The second benchmark also gathers some metrics around the throughput of the traffic generated. And here we can see that a slower eBPF program results in a lower throughput. The gain from the faster eBPF program was of roughly 20%, but this number tends to be less stable and, as a result, less reliable. For instance, we see a small difference between the two programs that were not really affected by the tail call optimization. Let's talk about future developments for the project. So the drawbacks we've seen is that we sometimes have various clusters of values using kernel probes because we cannot necessarily probe the ideal function. Also, using iperf between two namespaces introduces some overhead, and it's not always precise enough. And finally, ideally, we would have some more direct measurements for a specific instruction, for instance. In our case, the tail call instruction, the tail call set of instructions. Some things that were not explored completely were, for instance, using perf. At first, we did not go for this because it's quite difficult to isolate various eBPF programs using perf. But in the second benchmark, we are not isolating various eBPF programs either. And also, using the trace subcommand was deemed to be too much overhead, while using the record subcommand risks not giving enough information. So this could be something we could try more. We could also use the profile subcommand of BPF tool. It would give some more insight on the running eBPF program. And finally, we could improve the benchmarks I've just described using BPF stats, in particular the runtime NS values and the run CNT values. More details about the results and the experimental method are described in the paper of the conference. And finally, I would like to thank my colleagues in particular in the DOS and Unimog team for their help and support. If you have any question, I'm happy to answer.
Yeah, we can move this up to some Q&A at this point. I was just curious, did you consider using the trampoline mechanism with F entry, F exit that BPF has currently?
That's not something we have considered, but we could do it in the future, perhaps.
Yeah, because it's kind of designed for this kind of situation where you want to take a BPF program and do something before and after, and you could make measurements this way, and that presumably would solve the isolation, eBPF program isolation issue.
Okay. That makes sense.
We have a question from Paul Chignon. Asks, first says, thanks for the presentation, and then is the standard deviation reported in the paper the standard deviation of the averages reported by BPF prog test run? Did you measure the standard deviation of the actual run times, not standard deviation of the means?
So in the paper, I'm reporting averages over a few runs, 40 runs. For the first benchmark here, the standard deviation is of at most 1%, often 0%. And for the second benchmark, for the CPU time on this experiment, it's usually around 2 or 3%. And on the throughput experiment, it's higher, often 5 or 10%. Does this answer your question?
And specifically, they're asking, is the standard deviation coming from the one that's reported by BPF prog test run?
I'm not sure to see then. Could you please repeat your question?
They're asking if the standard deviation you reported is coming from the one that's provided by BPF prog test run, or did you calculate it independently on your own?
Oh, I calculated it on my own based on, I actually used the bench stat from the Go toolset because the results were gathered in the Go benchmark format.
And he says, thanks for the answer. So that's looks like it's taken care of. Do we have any more questions? I see some people typing, so let's give them a chance to ask their question.
Okay.
It's always a standard challenge to mimic production scenarios because there's all kinds of data structure accesses that are not present in the micro benchmark and so on and so forth. The iCache usage is significantly different, obviously. So it's really challenging to recreate accurate benchmarking of what will actually happen in production.
Mm-hmm.
Someone is typing a lot. Give them a chance to finish up. Paul's also asking, did you run BPF prog test run with more than 10,000 repetitions? They say, I did the same experiments and noticed lower values when running with repeat greater than 1 million. I'm guessing due to some cache effects that get amortized.
When I tried with more repetitions, the values tended to be stable and very similar to what I got with 10,000 repetitions or something like this. So for me, it was quite stable beyond the threshold I've chosen.
Good. Mache says, I think that benchmarks are the gap to be filled in general when it comes down to BPF programs. Personally, I've been using perf-stat for looking up the impact of tail call code related changes. So the question is, should we have something in the upstream that would act as a benchmark specifically? Like, do we need a generic way to measure tail calls or something like that?
That would be handy. On the other hand, it seems that we have, some improvements. There have been some improvements. So maybe something generic over various kinds of instruction would be ideal, as we would want to measure the impact of other changes in other parts of in BPF bytecode.
So following up to that, basically asking if you're planning to upstream some of your work, and John Fastaben mentions that we have a benchmark in self-test now, and he says he thinks it would be nice to add something there.
I've not discussed about with my manager about open sourcing part of the work, but why not?
Yeah, if you could isolate the test case into something reproducible and very restricted and specific, it could be useful for people.
Yes, that makes sense. Yes, it's a quite recent work over the last few months, and I guess the discussion about upstreaming this has not happened yet.
Good. Okay, there's not any more questions. We can. Paul Shingon is typing. It always says thanks for all the answers, and I'd like to thank you too for your presentation and the work that you did looking into this. Thank you very much.
Thanks for your attention, everyone. Thanks.
Okay, our next presentation is at 9:45, so we can kind of just relax here. Daniel also says thanks for the great presentation. We'll move on to the next presentation around 9:45-ish. Okay. Thank you, Clement.
Okay, bye. Thanks.
Let's take the presenter status. If you look on the list of users at the left side of your screen, you can set yourself, you set your status. I tend to set myself to confused because I'm frequently confused, but you can pick an emoji that matches how you feel right now. I seem to be the only person using this. All right, we'll be back at 9:45, so see you then. Okay, we'll start up in a few minutes. I don't see Denny here yet. Hopefully they'll show up in time for their presentation. Wow, some of you really noticed the poll button showing up quickly. Look at that. 9 of you, 10 of you. Okay, let's kill that poll. And let's load up the XDP offloading slides. Hey, Jesse, what's up? Denis isn't here yet. Yeah. Jesse, you're not giving this talk, are you? Okay, Denis not here, so we'll wait a little bit for them to show up, and we'll see what happens. If you're just joining us, we're waiting for the speaker to show up. They're not here yet. Let's just give them a chance. Maybe they're logging in right now and having some trouble. So we'll just give them a couple minutes. Hope they do show up eventually. I guess if we just, if we ultimately have a no-show, we could reschedule them for the part of the schedule on Friday that doesn't have any time taking up yet. So it's not a complete disaster if this should happen. Oh, Denny, there they are. Make them this presenter. All right, I've made you the presenter. You can control the slides and start giving your presentation whenever you're ready. Hello there.
Hello. Can you hear me?
Your sound's coming through just fine. Okay, you can start whenever you're.
Yeah, they think that I'm not sure how to show a presentation. So the bottom.
You can, if your mouse is on top of the slides that are in the dialogue, you can just do left and right arrows and change the slides.
Okay. So I pushed the restore presentation. So hope that everybody sees it on the screen.
It's showing up.
Okay, perfect. So my my today's talk is not mostly technical. I'm going to talk not from a technical side, but it's also important rather than the thoughts which I came to while implementing the XDP support for Xen NetFront driver. So basically, I've started with NetFront part, which is virtualized driver, which is put inside the virtual machine. So I've spent some time working on it, and it turned out that it works, but the performance numbers which I saw, I believe that it can be improved, obviously, because if we take, for example, Xen part, so we have two parts, one of the on the domain 0, another part which is a pure virtualized driver in the virtual machine. So they are connected through the shared pages and passes data between them. So initially I thought that it will be great to implement BPF support on the Xen NetBack side, which is the backend driver. Then it turned out that it can be solved by using by putting XDP support on a lower device, which is, so the basic scheme how it works, it just you have a bridge device, for example. So one of the possible configurations, you have a bridge device, the bridge device connects backend devices, and so that's how you connect all your virtual machines. So and I came to the thought that it will be great to connect to offload XDP from a guest to a host. So I started investigating. So came to the work which was done by offloading XDP to hardware, which Netronome successfully done. So, and after that, I came to the another work which was done by Jason Monk from Red Hat, and that's all. And this case is really similar to what I'm trying to achieve with with Zen. So so yeah, it turned out that currently there is no a core solution for that problem. So I also put to the slide that, for example, VMware virtual driver is on the way, and so the same problem can be solved there, and more hypervisors, which will definitely will appear in the future. So that's the problem that can be that may be solved. So in this way. So yeah, that's I wanted to discuss, because I followed through the discussion about the patches from Jason Wang, and it turned out that it's not so easy, since there's a lot of problems to not so easy to solve right now. For example, so that's 2 points actually which I came. So for example, for a guest kernels, we process each packet twice, for example, on the host side and on the guest kernel. That gives us a latency on data processing, and that gives also additional copies of a data, so which can be avoided. So yeah, the problems, they put some so that's some cases which I came not sure if they can be easily implemented right now. For example, if we take an immigration case, not sure if it's should be the first case to be discussed, but anyway, for example, we can switch to a different machine with a different CPU, with a different eBPF support features. For example, the kernel can be not the same version as was before on the host. So in my understanding, that requires some protocol to gather, for example, to gather information from a host system for example, the question here also about how we can, for example, offload per CPU maps, because in this case we have to share information, which obviously is not a good way to communicate between host and a guest. One way I was thinking is that we can design some kind of a protocol between that. So that's I wanted to discuss. So with the community probably. So I have no questions right now, and I don't want to. I mean, if everybody have nice ideas, that will be great. I mean, to discuss right now and to. I mean, not just lose time. I mean, implementing some features which won't be accepted for some reasons. So I think that's that's I put a reference probably. You're already familiar with this work. So is it worth, I mean, to try to work in a way which was initially started by Jason Wang, or not? So that's a good. What do you think? I mean, to keep trying to push. I mean, the patches upstream.
In the chat room, Christopher Clark asks, are you thinking about something similar to VirdIO's virtual device to driver feature negotiation?
Yeah, probably. So does it have some formal protocol? Actually, yeah, that's a good thing to look at, probably. Yeah, that's actually I've came to the conclusion. I came to the idea because it can be. It may be that hardware vendors can switch to, to making some capabilities in hardware that has some standard interface, but of course that's that will take a lot of time. To adopt this solution. If they provide some interface, so everybody can issue some commands, for example. But yeah, I believe it won't take place in the near future anyway. So definitely that can be somehow released, implemented on the software side. Moreover, most of the drivers currently, most of the widespread drivers, widespread hardware, most of the drivers for this hardware currently support XDP. So it's a really good chance that that underlying hardware will work. So the XDP. So another part, yeah, how to offload all this stuff, all these maps. Alexei Starvoitov also mentioned that it's really how to implement tail calls. Offloading tail calls from the BPF program. So
it kind of seems like if you would want to offload guest XDP processing into the host, there would need to be some hypervisor API for moving that state up back into the host, because the guest is where the XDP request will occur. Another idea is that if obviously this XDP program is attached to a virtual function of a NIC, I suppose that's where the API would need to exist for the VF instance to communicate with the PF instance to, push the XDP program up into the privilege level across the boundary of the guest. I'm sure there'd be some security considerations to go along with that as well. If you're moving a BPF program and its maps up into the host instance from the guest and the VF itself. So where to transmit this information, communicate to the host, what the guest would like to do with XDP is going to be a very important question in the design of something like this.
From the hypervisor side, it's also that nobody, that's a big question if Microsoft is going to release, for example. So there is not, or if we take VMware also, so there is no guarantee that the vendors will go and implement this feature. So definitely if it will be done, for example, in Zen or KVM, so, and the people will see benefit from it. So yeah, that's a really good chance that the proprietary companies will go and to implement this as well. But obviously there is no guarantee. Another point is that it can be some kind of standard or proposal for implementing such features for offloading, because so currently there is no such description. Except for we have a description how BPF works. We have a set of registers, we have a set of operands, set of operations, registers, vice versa, how the stack operates, but that's the internals of the virtual machine, but not for features which can be done. So also would be great to understand what community thinks about if it's worth to continue the work which was done by Jason Wang. I saw that the patches actually were sent a year ago, and I've not seen any follow-up from the submission, from the initial submission. So not sure if it's Jason here, but will be great to hear. Will be great to hear him.
I definitely think this work is valuable and useful. This idea has been proposed many times to offload guests' XCP work into the host, because there's obviously savings with avoiding the copying all these unwanted packets into the guest, for example, for denial of service protection and whatnot, and also avoiding all of the hypervisor context switches between the guests, the various guests. So it's definitely useful work. I think just someone needs to take, the existing work and actually follow up on it. And if the person who originally wrote it doesn't have as much interest in it, enough interest in it to continue updating and responding to feedback, someone else will have to take the lead and work with the patches and try to continue working on them. And as you said, think about what kind of interfaces need to be created for the different hypervisor technologies, as well as the different kinds of NIC drivers and virtual devices. So someone really needs to just take the lead on this. Someone who has the time and the interest at the same time.
Yeah. Okay. Nice to hear. So I believe that's all from my side. Yeah, that's that was not so long.
David Ahern states that the solution needs to consider resource accounting as well. For example, memory used by programs and maps. That's an important point. Yeah, if a guest pushes a program and associated resources up into the host, that needs to be accounted somehow.
Yeah, it's obviously one of the DOS vectors, right? So a guest can just push, just to create a lot of maps that just to populate all the hypervisor memory, for example. Probably that can be somehow limited. It is forced, for example, by some amount of memory, and then we have some kind of interface to adjust this value somehow. Yeah, probably a validator can solve that as well, but not sure. Forcing a memory. Forcing a memory amount, I'm not sure if it's really a good thing. Baking in the time, we can say, so you have just this amount of memory and that's it. Don't ever try to use more memory. So,
but the problem with that is that effectively, if you allocate a certain amount of memory usage to a guest, with this facility of XDP guest offloading, you could effectively use twice as much as you've been allocated, because you're using that memory space on the guest to put the program and the maps together, and then you're making the host eat up a copy of that as well. So it's you really do need to take it into consideration. We need to limit it somehow. Stephen Heminger makes comment that there also needs to be tighter security model. Just a BPF validator is not enough to allow a program to run in host context. For that, I would say yes and no, right? The validator does provide a certain level of protection as to correctness and whether accesses are valid, but perhaps there needs to be a higher level of control, like like, okay, this is related to BPF program signing, another thing that will be discussed in this summit. Perhaps people would only want to allow guest offloading for signed BPF programs that meet a certain criteria and then been validated by the cloud provider or whoever runs and controls the infrastructure. So there are very serious security considerations once we start allowing arbitrary programs to get pushed up into the host.
Yeah, the last comment from David also makes sense, since that's unclear what to do in such case. I mean, when we have a different routing information on a host, so
we would probably have to disable helpers down to a very minimal set of helpers that are only relevant for the packet context itself and not accessing data structures in the kernel that would be contextual. And that also gets us back to security considerations. Again, we could leak host info into the guests indirectly by allowing them to call certain helpers.
Yeah, okay, yeah, that can be a solution. Sure, definitely. If you want to just run on I mean, not in this case, you have to work on an original device, so without offloading, so that have to work.
Mm-hmm. It almost seems like we would need a context when we run a guest program that would, somehow. So if we're using a namespace, it seems interesting that if we would push programs from a namespace into the root namespace,
Mm-hmm.
the root namespace has access to all the data structures that the XDP program has in the sub namespace. You see what I'm saying? So technically, we could actually execute the XDP program from the guest, accessing that namespace's data structures when it makes helper calls. This is not an option we have when we have physical separation, as in the hypervisor case, but it's something to think about that would allow certain kinds of moving programs around, yet accessing the same actual kernel data structures that are relevant for that context. Toke asks, what about execution time? A full 1 million instruction XDP program can use up quite a bit of CPU in the host context. Yeah, that's an interesting concern as well, like what we could do about that. Perhaps have a guest limit on XDP program size for this offloading case.
Yeah. So I also, the relevant question here is about, so what if is it really I mean, not all programs can benefit being offloaded, right? So, so that can be some kind of heuristic model, probably. That's not a good at all. But for example, if we have a lot of accessing, I mean, data accessing through the maps, so not sure if we really get benefit being offloaded. For example, one really good case, it's implementing some kind of packet droppers, so some kind of firewalling. So also, I mean, redirecting packets also can benefit from that, from being offloaded. That's I'm seeing right now. But definitely there are some cases which won't benefit from that. So it's really a good thing to think about. Yeah.
Another interesting issue brought up by David Ahern just now is that we might also want to account the execution time if XDP is executed in software on the host on behalf of the guest, how to allocate the execution time to the guest properly, because technically we're eating CPU cycles that the guest would have used. Right. And Alexander Graf asks, he says, the whole point is to copy less data, right? In this case, we copy less from host to VM. That's the first step. With BPF programs on the NIC, we would remove the NIC to RAM copy as well. Could we push further and do filtering on the network fabric already? That's like another level. Like, how many levels of indirection can we push an XDP program in the guest? This also goes into the discussion of infrastructure. Like, if you have a big piece of deployment and you're trying to do DDoS protection, do you have a centralized database, or do you allow the individual cloud guests to have their own denial of service bad IP address database that they implement locally? And that's why XDP guest offloading would be useful. The other aspect to this is we would like the flexibility is nice to allow any guest to do whatever they want to do with XDP, be it filtering, forwarding, load balancing, whatever, and then the host would optimize that network data plane path for them by this offloading aspect. And in what environments are you comfortable with allowing this? So there has to be some kind of control, some kind of security issues. And then we go to the Alexander's Graf's question, well, shouldn't some of this stuff get pushed all the way into the network fabric and not actually execute on the host or the guest at all?
What I'm really trying to get to is, I think the idea is much bigger than just hosts and guests, right? We're just really talking about pushing BPF applications to higher levels up the stack. And I'm not sure where that actually ends. The network fabric is just one idea, right? You could, for example, think that you want to execute some basic filtering already on your network endpoint, right? Where you connect internet traffic to internal traffic. If you could filter there already, that could reduce a lot of costs in your internal network routing. If you, for example, have a DDoS attack. So whatever you're designing, I think if you really want to take up the task of pushing patches like this forward and doing XDP offload with the guest, I think it makes sense to have that in the back of your mind, that maybe we want to push further than really just host-guest relationships. We maybe want to, like the host and like putting it onto the NIC pushing is like absolutely in scope. If you look at all the Freescale QRQ series, you basically have completely OS definable applications throughout that whole stack. That's the whole design of this chip. All of the Mellanox adapters work basically the same way, just that you don't get access to the code. So that's a bit harder. I know that we at Amazon have NICs that are basically just software. We could do anything we want there. We could run BPF applications if we wanted to. I'm pretty sure others have very similar techniques and could do similar things.
So, yeah, so the question is, if you're pushing it into the fabric, how do you allocate and control resource usage, which is the same as the host problem, offloading to host problem. So you would have to solve that somehow, because you don't want all of your cloud guests using up all of your network fabric resources, doing all this complicated XDP stuff with no limits whatsoever on a per guest basis.
Yep, exactly. But it's what we're basically agreeing on is it's the same problem regardless of which level you put it onto.
And it has the same set of issues with defining APIs and how to move this information around, how to move the maps, how to move the programs, and what kind of security issues need to be addressed as well.
Yeah, Tom was bringing up a good point there where he's saying smart things are relevant. You could probably implement the hardware offload on smart NICs today. Like if you, for example, take one of the current Mellanox smart NICs, you have a data filtering path on your card that you can completely control by software. So you could probably implement the whole thing even in a hardware-based solution if you wanted to. I'm not saying you should. I think it's perfectly reasonable to implement it in a virtual machine because it's a much easier environment to reproduce. But we shouldn't limit our interfaces and APIs and thoughts to only host and guest relationships.
Yep, for sure.
Longer term, we should also consider this for the whole fabric, like integrating with a programmable network in the whole data center or whatever, and figuring out how to move things between HTTP and P4 and all this stuff.
And a lot of situations you would see that people would come up with their own internal solution for doing this kind of stuff. I mean, abstractly, it's almost like what Cloudflare is up to, right? Except we want like to formalize this in some way, to have a way to have programs applicable to certain guests, but actually implemented at the ingress, whatever that might be for where this cloud stuff is happening. So yeah, it's a really interesting point. Richard Prasad says there are different attack surfaces in each context. Yeah, it's very true. So the issues that we would have to address on the host level versus guest would be different from a network fabric context. So different set of problems to solve, different set of attack surfaces to address.
There's also the question of how you discover what you can actually support in the offload. Like if the hypervisor kernel is way older than the host kernel. Sorry.
Yep. Yeah. What set of features are supported on the network fabric XDP implementation?
Yeah, but this is not different from hardware offload. So I think the parallels between just offloading to hardware and offloading from guest to host is very much sort of the same problem.
Mm-hmm. So maybe since we haven't fully solved the feature detection issue yet, we now have the foresight to consider the network fabric level of that problem space as well before we implement anything.
Yeah.
Okay, cool. If there's any other questions, I should bring them up now. It's a very interesting topic, because we've been talking about this for a long time. It was imagined a long time ago that, hey, we should avoid the hypervisor overhead if we have an XDP program running on the guest, and how could we do that? And I'm glad that people are looking into this and thinking about it seriously, and to a level even higher in the network fabric case. So it's really good to see people talking about this. I don't see any more questions, so Denis, thank you very much for your talk.
Thank you very much.
You're welcome. So that's it for today. Things went relatively smoothly, I thought, except for the little hiccup at the beginning where the slides were not showing up in the YouTube live stream, but that's been fixed now. Guy took care of that for us. And see everyone tomorrow, bright and early, well, at least for us on the West Coast. And we'll start with The Way to the DPath Helper by Jira Olsa, and that should be really exciting. Otherwise, have a great day, get some rest. I know everyone's brain's tired from sitting and watching presentations for a couple hours. I am as well, probably take a nap. But thanks again to everyone who presented today, and I look forward to seeing everyone tomorrow. Take care.